So next topic is how to find connected component in graph. So first of all, you try to understand if every vertex is reachable from each other. Let's say vertex 1 to 2 you can get, then 4, then 5 and 6. Then at max we have one component in the graph. So this is the one thing. If all the vertex you can reach from one vertex to another, then that graph normally has one component. So roughly graph, whatever normal graph we see, they normally represented as a single component. But there are chances when your graph has a different component or more than one component. So how to calculate how many number of components your graph has? So it depends on, so that's the reason this is normally connected component is not known as a normal graph. It is known as a subgraph. So your original graph is super graph and your connected component is a subgraph. So your subgraph may or may not be connected with all the vertex. Fine. So let's say this is the subgraph of my original graph. Then all the vertex are connected. Then we can say this is a subgraph of my super graph G, where connected component is 1. So let's say we remove this edge, this marked edge. I am telling you to remove it. If you remove it, how many component you have? Now in that case, it's become two subgraph. One subgraph will be this one, and another subgraph will be this one. If you remove this particular edge, then in that case, these are basically two subgraph of original graph, and we have two connected component. And let's assume you have removed this edge also, then definitely you will have three component of your graph, because there are three vertex. This is a separate vertex and these four vertex are connected. So the original graph may be having everything connected, but subgraphs are three in component. So that's the basic definition of connected component. It basically nothing, it's a subgraph from a main graph where every vertex is connected to each other. So this is the definition written there. The things I have explained to you. So connected component is a subgraph in which every vertex is connected by a path. Okay. And second important point, no vertex in connected component with any other vertex in the supergraph. Definitely every vertex is separate. Then if there are two component, then no vertex is connected with any other vertex in the supergraph. And how to find out? Basically we write an algorithm to find out the connected component, how many connected component in my graph. So that algorithm basically use either DFS or BFS, and if we are using BFS or DSF, they are called recursively to find out how many connected components are there in your graph. So that's the next important point. In order to design any algorithm to find out how many connected component your graph has, we basically use BFS and DFS algorithm. This is one of the application of BFS and DFS also, to find out whether graph is connected or not. And how many number of times you need to run this particular DFS and BFS, that basically depends on number of recursive call. Let's take an example. Let's say there are these are three different subgraph of original graph which has 8 vertex. Then you need to run DFS over this 8 vertex. How many times? Recursively you need to run 0, 1, 2, 3 first. So this is one connected component you will get. Again you will start DFS from starting from 4 and traversing to vertex 5. So it will give you another count, that is count number 2, second connected component you will have. And then again you need to call DFS starting from 6, 7 or 8, and then you need to find out as a third component. So you will run your DFS algorithm or BFS algorithm, and accordingly you will get how many number of connected component in the subgraph of original graph having 9 vertex. Let's say 0 to 8 means 9 vertex. Then you will have 3 connected component. So how basically algorithm works, I am going to explain you details step by step in next portion of this video. So roughly if you say the same questions we can take for solution. The initial algorithm takes every vertex has a weight of -1, means none of the vertex has been visited by DFS. So flag we will be setting like -1, -1, -1 everywhere. We will be setting what? -1 value to all the vertex, and we can start our DFS from any particular, let's say, vertex. Let's say DFS is starting from vertex number 0. So once we have visited this vertex, we'll make flag of this vertex as 1. This is the strategy of algorithm. So we will see the algorithm and how basically it works. I'm just going to tell you. So see the connected component graph algorithm for each vertex V which belongs to maximum number of vertex n in our algorithm. So take an example, same example. Let's say we have, and how many vertex are there basically. So we have 0 to 8 vertex are there. So now n will be what, basically 9. So for each vertex V which belongs to n, maximum number of vertex in my particular graph, set flag V equal to -1. This is my first step. I have explained to you that flag you will be setting as a false here, means none of the vertex has been visiting. False, you can set either 0 or -1. Okay, initially you have not counted any component of the graph, so counter value you will take as a 0. Now you will run a loop, and loop will be starting from, let's say, V vertex 0, let's say is my source vertex for DFS I have chosen. Okay, and starting from 0, and then we will be going to all the vertex, that is V is less than n, to 0 to 8 will be moving, and then B plus plus. Let's say in for first step V will be 0. Initially flag I have set as a -1. I will be calling DFS algorithm. From this line I will be calling vertex V is 0, so DFS over 0, and flag is -1 right now. So we will be calling DFS on this particular, let's say, 0 vertex. Okay, and from this vertex flag to all is -1. First of all I will be calling DFS starting from this. Same algorithm of DFS will be working, and from this line onwards counter will never go to, let's say, counter will not go to next to this line. It will call another function, that is DFS here. So DFS is calling over vertex 0, and right now flag is -1. First of all, now vertex V has been visited, so flag of V will set as a 1. Okay, so whatsoever vertex we have visited, initially it was -1, later on we will make it to 1. We will print that vertex in cout, or you can say printf statement, that this is the value of vertex. So what will be the printing statement here? This will give you 0 right now. And now for each adjacent node U of V, we will set flag of, if there is flag of U equal to -1, we will again call DFS. Okay, so let's go to the questions. We will go to 0, we will find out the adjacent of 0, that is 1 and 2, and its flag is still -1, so we will call flag on the adjacent variable using this again recursive call. So either we can call 1 or we can call on 2. Let's say I have gone through this vertex, so again DFS will be called over 1. So DFS will be called over 1, so this algorithm will be called, come back to this. Okay, and this will be printing in the same way. Again DFS will be called over, let's say, 3 and then 2, and once 0, 1, 2, 3 has been visited, all these flags will become 1, 1, 1. Okay, after visiting this you are setting this and printing this, and at last what will be the value here? Now once 3 will be, let's say, visited, it will return, it will go to find out its adjacent, and let's say adjacent 1 and 2 already been visited, so it will give the control to this line. Okay, after this line control will come back to. So you can see one more thing, that here V will not go make to 1 here, because V is last V was my 3, so it will be make it to 4. So starting will be next, V will be starting from 4th vertex, that is our vertex number 4. Fine. So this V is still less than n, that 4 is less than n, so I will start from 4. We will go in the same way, 4 to 5, and then next time 5 will become 6. So 6 is still less than n. We will keep on running our DFS 6, 7, 8. Once all the vertex has been visited and marked as a 1, let's say all the vertex has been visited and marked as a 1. After this counter value will become 1. After this counter value will become 2, and at last after visiting all 3, counter value will be 3. Okay, and at last you can see the condition become false. 8 plus 1 is 9, and 9 is not less than 9. So at last it will print the number count, and count is 3. So in this way you can calculate basically the total number of connected component in your subgraph of a given graph. So if all the vertex are connected and traversing through DFS, it will give you answer 1. If vertex are not truly connected, we will call DFS again and again, and we will get a counter variable, and we will get the answer as a 3. So this is all about what? How to find out and how to write an algorithm for connected component using VFS or DFS. Thank you.